Hello, the title of this paper is Small Object Matters in Weakly-Supervised Semantic Segmentation. I'm Cheolhyun, the presenter. The order of today's presentation content is as follows. The goal in the field of Weakly-Supervised Semantic Segmentation is to perform pixel-wise classification using a model trained with weak labels. In other words, it involves learning from labels such as images, points, or bounding boxes, rather than labels at the actual pixel level that needs to be predicted. In this paper, we discover shortcomings in the intersection over union metric commonly used in the segmentation field. This metric has a problem in that it does not effectively reflect the overall understanding of the scene. As illustrated in the example, assuming the same number of matched pixels, both cases of correctly and incorrectly predicting a small object would yield the same result. However, predictions 1 and 2 clearly differ in terms of the overall understanding of the situation, and the IOU metric fails to distinguish between them. Next, this study illustrates the imbalance in datasets used to evaluate existing segmentation models. In reality, some samples consist of a very small number of instances with extremely small size. This issue highlights the difficulty in accurately evaluating performance, especially for small-sized objects. This section covers the methods proposed in this study. In this section, I will explain the proposed metric, dataset, and loss functions in the study. Before explaining the newly proposed metric, let me briefly describe the issues with the existing MIOU metric. The calculation method of MIOU considers predictions and ground truths for each class as a single set, regardless of individual object as mentioned earlier. In this case, the metric distributes the importance of each pixel equally. Therefore, to mitigate the aforementioned issue, the study proposes a method to measure IOU for each object individually. The measurement approach is as follows. Unlike MIOU, we calculate IOU after dividing objects within the same class. This allows us to consider equal importance for each object, regardless of each size. However, as mentioned earlier, to enable object-level measurements, both the ground truth mask and predictions must be structured at the object level. Firstly, for the ground truth mask, we insert object-level ground truth mask by using instance-level mask in the evaluation, rather than the class-level mask commonly used. Next, since the conventional prediction mask is also predicted at the class level, we first outline the predictions to form object-level prediction mask. Subsequently, we consider two cases. The first case is when there is only one corresponding ground truth object for a single prediction object. In this case, there is no need to separate the prediction, and we can directly calculate the IOU with the corresponding ground truth object. The second case involves situations where a prediction object corresponds to two or more ground truth objects. In this case, we need to split the prediction object to match each ground truth object. As illustrated in the diagram, in the second step, we calculate the number of pixels in the overlapping region between each ground truth object and the prediction object. In the third step, based on the ratio of these pixel counts, we divide the remaining non-overlapping regions to ensure that the prediction object is divided and corresponds to each ground truth object. This approach transforms the class-level prediction mask into an object-level prediction mask. Through toy experiments, we confirm that the MIO metric shows biased results toward larger objects. In cases A and C, the score rises sharply as the prediction result for large objects improve. Particularly in case C, despite correctly predicting all small objects, the score remains low. However, as the result for one large object improves, the score rises significantly. Similarly, in cases B and D, even when the result for small object improved, it is not well reflected in the MIOU metric. On the other hand, our metric instance-aware MIOU clearly demonstrated consistent result regardless of the object size. Furthermore, when experimenting with actual benchmark data, we observed a different trend from MIOU as shown in the right graph. Next, we analyzed the shortcomings of existing datasets and proposed a new evaluation dataset. Firstly, the widely used PASCAL VOC benchmark is observed that objects with larger size occupy about half of dataset. We believe that when evaluating with imbalanced datasets like VOC, it is challenging to achieve reliable results. Therefore, to address these issues, we created a balanced evaluation dataset. The process of constructing the dataset is as follows. The final completed dataset consists of 1,137 images and includes 20 classes. This dataset is designed for evaluation purposes and can be used to assess models trained on PASCAL VOC. Lastly, we proposed a training method to effectively capture small-sized objects. Upon examining existing methodologies, it was evident that the most improvements were made in stage 1 of the training process, which makes pseudo-mask for training semantic segmentation networks. However, there is a problem with the cross-entropy loss used in the segmentation network, which can lead to imbalanced learning. In the training process, pixel-wise losses are calculated to optimize the model, and then the average loss is used for backpropagation. This results in a higher impact on the loss from larger objects with more pixels, making more challenging to train the model effectively on smaller objects. To address this, we designed a size-weighted cross-entropy loss function, which considers the size of object and assigns weight to pixel-wise losses. We also consider the difficulty in training the model on larger objects due to size-weighted loss function. Therefore, the final proposal is the size-balanced cross-entropy loss. Initially, the model is trained using the conventional cross-entropy loss to allow some bias toward the larger object. Then we use our proposed loss function to fine-tune the model. To prevent the model from being optimized exclusively for smaller objects, elastic weight consolidation is introduced. Next is the experimental sections. The experimental settings are as follows. Here are the experimental results for PASCAL VOC and PASCAL B dataset. The evaluation was conducted using a model trained on PASCAL VOC dataset. Firstly, in terms of metrics, when evaluated with the newly proposed metric compared to the conventional MIU metric, a general decrease in performance is observed. This is because our metric reflects the performance of each object equally, resulting in a better representation of the performance of smaller objects, which tend to have relatively lower performance. A similar trend was observed for the PASCAL B dataset. Due to an increase in the number of smaller objects compared to VOC, the overall performance is lower than PASCAL VOC. Next, when using our proposed loss function, an overall improvement in performance compared to the baseline was observed. Notably, the performance improvement was evident not only for small objects, but also for all objects. Furthermore, we apply our proposed methods to models based on fully supervised learning, and similar results were obtained. Finally, here are the visualization results for the PASCAL VOC and PASCAL B. In conclusion, this research aimed to address the issue of existing methods not effectively capturing small-sized objects. To overcome this, we proposed new metrics and a balanced dataset. Furthermore, we introduced a new loss function and validated our proposed methodologies through experiments on several datasets, metrics, and multiple models. Thank you for interest for our paper. For more information, please refer the paper.